This video is for section 6.3, the binomial distribution, and this is a type of problem you actually saw in Prob Stat. And we're going to look at similar problems as you did in freshman year, but now we're going to look at them through a more sophisticated eye. So take a minute and read the example here. We have a manufacturing plant. There are some defective parts. The probability of having a randomly selected defective part is 15%. We're going to take a random sample of 8 parts. We want the probability that exactly 2 are defective. And then later we're going to look at the probability that 2 or less are defective. If this kind of problem seems familiar to you, these are the type that we did in Prob Stat. But the idea here is, so imagine that we have 8 parts. Okay? Some of them could be defective and some will be good. So for example, imagine that these 3 are defective. Or it could be the next time we do it, perhaps these 2 are defective. Or maybe the next time we do it, we happen to have a bad lot and maybe 5 of them are defective. So out of the 8, there's different probabilities that different numbers of the parts are defective. I want the probability that exactly 2 are defective. Okay. First of all, we need to examine this problem. This is a problem that is considered a binomial distribution problem. And there are 4 things that make this binomial. You do need to memorize this list and be familiar with it, and they follow your notes exactly here. A setting is considered binomial, first of all, if each observation falls into one of just 2 categories, success or failure. In this situation, when we're checking parts, they're either good or they're defective. There is no third category. Number 2, there are a fixed number of observations. In this problem, we are checking 8 parts and only 8 parts. The number of observations could be different from problem to problem, but in this problem, we're looking at 8 parts, fixed number of observations. Next piece, the observations are independent. This means that whether or not a part is defective, does not depend on whether the one previous to it was also defective. So the observations are independent. And finally, the probability of success is constant. It doesn't change. In this problem, the probability that a part is defective is 15%. Okay? So some stuff here. If we satisfy all 4 of these things, we say that x, the number of successes, is called a binomial variable, and we have some notation for it. Keep in mind that we had notation symbols for a normal distribution. Now we have a binomial distribution. So here, if we say x equals the number of defective parts. Defectives? Not. This means that x has a binomial distribution, big B for binomial, and we use the letters n and p inside the parentheses here. Just like we had mean and standard deviation before for normal distributions, here we're going to have n and p. So we say that x in this problem has a binomial distribution. We're checking 8 parts with a probability of success of 15%. Okay, just some new symbols here. So we're going to go ahead and tackle a problem. I'm going to dive right in and give you the formula that is given to you on the AP exam. It's this nasty looking formula right here. Okay, and it may look a little intimidating, but I think when you start going through it, it's the same stuff we did in Prob Stat. So let me walk you through it here. So we know that x has a binomial distribution. We're checking 8 parts with the probability of success, 15%. I want the probability that x equals 2, that we get 2 defective parts. I'm actually going to show you the way we did this back in Prob Stat. Back in Prob Stat, we would have you set up 2 sets of parentheses. Tell me when this comes back to your memory banks. 15% is the probability that a part is defective. 85% is the probability that one is not defective. In this problem, I'm looking for 2 defective parts. So I need 2 of these guys, which means the remaining 6 will be not defective. And the last piece of the puzzle, if you look at the formula, is this right here. Don't be worried about this. This is just a combination. This is the same as NCK, if you remember combinations back from Prob Stat. And what the combinations do is it takes care of all the different ways that the defectives could be mixed up with the good parts. And in this problem, it's 8C2. So at this point, you're going to have a lot of calculator practice. You should go ahead and pause the video, type that into your calculator, do the practice with the exponents and the combinations, and you should find that the answer is 0.2376. So it is a problem that we did in Prob Stat, just coming back to revisit us again. Let's do the second half of the question now. Now, what is the probability that 2 or less are defective? Well, 2 or less means that we could have 2 defective parts, but we could also have 1 defective part. We could have 0 defective parts. And we need to take these 3 outcomes and add their probabilities together. Now the good news is we've already done the probability of 2. it's 0.2376. Let's very quickly walk through the next two. The probability of 1 being defective, I need 2 sets of parentheses. 15% probability we're defective, 85% probability we're not. I want 1 defective, which means 7 not defective. And we'll also put that combination in there, 8C1. Finally, the probability that we have 0 defectives, again, 2 sets of parentheses, 0.15, 0.85. I want no defectives, 8 good parts, 8C0. That's supposed to be an 8. Lost my equal sign. 8C0. There we go. And you would add all these outcomes together. Now, I'm going to leave the work to you to add these 3 outcomes together, but you should see that the answer comes out as 0.8948. So there's a little calculator practice for you to verify that solution. Okay, next piece. So if we have a distribution, we are interested in the mean and the standard deviation of the distribution. So now we're talking about cars here. Here's our new scenario. We have cars going in for inspection. 30% fail the inspection, and we're going to check 50 cars. How many should we expect to fail inspection? Well, this is really an expected value problem, and the expected value is the mean, and we have formulas for mean and standard deviation here. They are given to you on the AP exam, and here they are. We see here that the mean of x in a binomial setting is given to you by NP, and we have a formula for the standard deviation as well. So let's put it all together. Again, we have, in this problem, we have x is binomial. We're checking 50 cars, and the probability that a car fails inspection is 0.3. So actually, it's interesting here. We're defining x as it fails the inspection, because that's the number that's given to us. Inspection, that says, if you can't read it. Inspection. Okay. And I want the mean and the standard deviation. Well, I'm just going to use the formulas. The mean number of cars to fail the inspection is 50, which is n, times 0.3, which is p. Put those into your calculator blender, or actually do it in your head, 15. On average, in a group of 50 cars, we should see 15 that fail inspection. How about the standard deviation? Again, we're just going to use the formula that we're given. It's a square root. It is n times p times 1 minus p. Here n is 50, p is 0.15, and 1 minus p is 0.85. You notice these are just 2 numbers that have to add up to 1. Put those into your calculator. You see that the standard deviation comes out as 3.24. So in groups of 50 cars, on average, we should see 15 that fail inspection with a standard deviation of 3.24.
So hi gang, before we end this video, you may have noticed a small error in the last computation here for standard deviation. Notice in yellow here I have probabilities of 0.15 and 0.85. Those were the probabilities from the previous problem about defective parts. Here in this problem about cars failing inspection, I really should have 0.3 and 0.7. So just a small little boo-boo there. You do get the correct answer of 3.24, so make sure you make that correction in your notes. And this is the end of the binomial probabilities video.